Welcome to my channel, everyone. Today, I'm reviewing a new product from FNIRSI. This is a 4-in-1 device. The model is called DPOS350P. And this is the most expensive, most advanced oscilloscope, and not just an oscilloscope, from FNIRSI. Well, as of the time this video is being filmed, it's early summer 2025. The price is about $250. The price may change depending on various discounts and on when you're watching this video. As you can see, this is a tablet oscilloscope with a fairly large, high-resolution display. It's 7 inches. When you pick it up, it immediately feels like a truly serious product because it has some noticeable weight to it. These side parts are actually made of solid metal. If FNIRSI really managed to deliver everything they claim for around $250, and by the way, in terms of hardware, this is a very, very serious and impressive device, then this device will definitely make a real splash. Because I took a quick look at what it can do and used it a little, and I was genuinely impressed. It's super convenient to use, except for the awkward Russian translation. But that's forgivable. It can be fixed with a software update. I haven't fully tested it, and unfortunately, I don't have the ability to check the claimed maximum specs since I don't have a high-frequency signal generator. But we'll definitely test everything we can. If you compare the size to the previous oscilloscope from FNIRSI, which is actually pretty good, portable, and relatively inexpensive. Plus, this device isn't just an oscilloscope. It's also a signal generator and a multimeter, basically an all-in-one tool. Next to this new device, the old one really looks tiny. So let's go ahead and start with what's included in the package. It comes in the classic, well-known FNIRSI box. Here are the features that are listed on it. Excellent. Great picture. And really, you can more or less display all of this, and by the way, show it on the screen. By the way, the technology here, I actually showed another oscilloscope from FNIRSI. It's an electronic device. What were they called again? Do you remember? Basically, phosphor oscilloscopes, something like that. Well, the picture is pretty cool. It has something similar to that afterglow effect. So this is what the box looks like. All the main specifications are listed right here. If you look at the manual a bit later, I'll show you the main focus is really on the oscilloscope. Well, the other 3 options are here too, which is nice, but they're pretty basic. But the oscilloscope here is actually quite serious with a lot of settings. Next, there's this really cool carrying case. You can fit all the accessories in here, and there's still room left for a small multimeter. This is what it looks like. So included in the set is a very flexible USB Type-C cable, like this one, for charging and syncing with the PC. Alright, let's set this aside for now. I've already opened everything up here. Here are our probes or test leads and accessories for the probes. The probes themselves are actually of pretty decent quality. But again, you have to understand that they're budget items. These are consumables, so it's important to keep that in mind. If you need something more serious, better, and more expensive, there's nothing stopping you from buying it. The probes here are rated for 350 MHz. Man, why did I think they were rated for 400 MHz? So, a pair of these probes, since our oscilloscope has a bandwidth of 350 MHz. But that's in single-channel mode. In dual-channel mode, it's a different story, which I'll show a bit later. Next, this is the charger. The device supports fast charging. It has a pretty high-capacity battery. Naturally, it's portable and battery-powered. So the charger is 18 watts and can deliver up to 12 volts. In other words, it supports fast charging protocols. There's also this cheap little thing. It's for connecting to the signal generator. Yes, that's included here too, and once again, it's quite high frequency. And of course, there's the manual. Product manuals from FNIRSI have not included Russian for quite some time now. So the FNIRSI DPOS350P is a 4-in-1 device. As I mentioned earlier, It's a 2-channel oscilloscope with a bandwidth of 350 MHz and a sampling rate of up to 1 gigasample per second. It's also a decent signal generator. There are a lot of different signal waveforms available here. It's a spectrum analyzer. Yes, they included a spectrum analyzer in this device. And it's a frequency response analyzer. That's the fourth option. I'm not sure how useful a spectrum frequency analyzer will be for the average person. If you do use analyzers like these, you should understand that these are, let's say, very limited analyzers and are more like extra features rather than full-fledged instruments. As I mentioned earlier, the main focus here is definitely on the oscilloscope. The signal generator is secondary. And everything else, in my opinion, is more for marketing purposes. But the devices are fully functional. So let's start with an external inspection. As I already mentioned, the device is quite hefty. It stands steadily on the table. There are these protective bumpers. I don't really know what they're for. Most likely just for looks. But it also has these rubber feet that prevent the device from sliding on smooth surfaces. So you can use it without any issues. On this side, there's a stand that keeps it stable. Well, it has one stable position, and the angle is actually quite comfortable and convenient for working. So, for extra clarity, here are its main specifications. There's a fan here. Apparently, the internal components heat up and need cooling. And the fan is actually pretty noisy, you could say. Well, desktop oscilloscopes also have cooling systems. And it's fine, really, you get used to it. On top, we have bayonet connectors. These are for the oscilloscope inputs and the signal generator output. On the side here, we have a Type-C port for syncing with a PC and for charging. There's a power button. These little triangles here, that's the lighting. I'll turn it on in a bit, and you'll see for yourself. On this side, there are only the triangles. That's clear here, so that's it. So as for the controls, or more precisely the presence of buttons, everything is clear and simple. There's just a single button, and that's how you start this thing up, and it boots up really, really fast. Now I'll be quiet for a moment so you can judge the noise level. A bit later, I'll probably bring a sound level meter so you can see the numbers and get a clearer idea. I think it's actually a bit louder than my desktop oscilloscope. Well, you can get used to that in principle, but here there's a gorgeous, gorgeous display, excellent viewing angles. Everything is really beautifully done. Although I already have some nitpicks about these small settings. Damn! I really do wish there was some way to make the sweep parameters just a bit bigger. My eyesight isn't all that great, so I often find myself having to squint and strain just to see anything clearly. Alright, but that's not actually the main point here. There are icons everywhere here. As you can see, we've just turned on the first channel, and for now there's no signal. Let's set all this aside and take a look at the main features of this device. Here are the main specifications of the device. These are the languages supported by the device. Russian is among them, so the only place Russian is missing is in the manual itself. Otherwise, you can set the device's language to Russian. It has a 7-inch display with a resolution of 1024 by 600 pixels, an IPS panel with good viewing angles, and a capacitive touchscreen. You can set the auto power off from 15 minutes to 1 hour, or turn it off completely. As for the firmware, it's not really a concern. The battery here is a lithium-ion 3.7 volts, 8 amp hours. A quick charge charger, 18 watts or 12 volts at 1.5 amps, is included in the package. Well, as for the charging time and standby time, that's clear. We can also see the power consumption here. It has active cooling, and here are the device's dimensions and what's included in the package. And finally, the oscilloscope specifications. I'll just point out the most important things you need to know here. This is a 2-channel oscilloscope with a bandwidth of 350 MHz and a sampling rate of 1 GHz, or 1 gigasample per second. To be fair, I should note that most manufacturers specify these parameters for single-channel operation. You need to understand that if it's a 2-channel or 4-channel oscilloscope and the channels are running simultaneously, these parameters will be significantly lower. The rise time is 1 nanosecond, which is really impressive for an oscilloscope in this price range, especially considering that this device is not just an oscilloscope. And overall, if you look specifically and carefully at the bandwidth and the sampling rate of 1 gigasample per second, there really aren't that many options available on the market at around the same price point. I'd even say you probably won't find any at all. Memory depths, input impedance of 1 megam, capacitance of approximately 14 picofarads, as well as the horizontal sweep time, which ranges from 5 nanoseconds to 50 seconds per division. This means we can study very slow processes, for example, and if you really want to, you can even do some relatively long-term monitoring over a period of time. So regarding the sweep time, moving on. As for the vertical sweep, it ranges from 2 millivolts to 20 volts per division, assuming the probe is set to 1x. So 2 millivolts is more than enough. In other words, the oscilloscope sensitivity is really impressive. It's enough to study even very small voltage ripples. For example, if you need to examine highly stable power supplies, this is actually pretty good, as it provides the necessary accuracy and stability for such tasks. So that's about the measurement accuracy, the input, and the probe, which are all important aspects to consider when assessing your equipment. Well, I don't think there's any need to explain further. If you set a certain divider on the probe, you also need to set the corresponding value in the oscilloscope software so that it calculates the vertical scale parameters correctly. Here we can also limit the bandwidth. The limits are set right here. There's also a high-resolution mode available, up to 16 bits. That's pretty tempting. So it can measure 12 different parameters. There are also cursor measurements. Here are the things we can measure using the cursors. Now about the trigger mode. You can set the trigger for either the first or the second channel here. The standard trigger modes are normal, single, and auto. Accordingly, you can trigger on the rising edge, the falling edge, there's auto adjustment of the oscilloscope trace, and you can set the trigger level. We can save up to 90 screenshots and up to 500 signal waveforms. There's nothing particularly special here. Well, I'll note that, as you'd expect from a 2-channel oscilloscope, it supports XY mode. So, if needed, you can study, for example, Lysagis figures. Here you can zoom in on a specific area. In other words, there's a general zoom function. And that's probably all you need to know about the oscilloscope. Now then, on the other hand, no, this already concerns the signal generator. The signal generator is pretty basic, and it's immediately clear that this is again a secondary feature, because there's no detailed information. From what we do know, the generator goes up to 50 megahertz, but that's only for sine waves. For other waveforms, depending on the shape, the maximum is up to 10 megahertz. As for amplitude, we can adjust it from 0 to 5 volts peak to peak. The resolution is 1 millivolt. Regarding duty cycle, everything is standard. The resolution is 0.1%. Well, that's probably it. We'll cover the rest in practice. As for the spectrum and frequency analyzer, we'll look at that separately in detail at the end of the video because, as I mentioned earlier, it's more of an auxiliary or supporting feature rather than a full-fledged primary measuring tool. And in most cases, I'm quite sure in probably 99% of cases, everyone who decides to purchase this device will get it specifically for the oscilloscope functionality, and of course for the built-in signal generator as well. But again, the main thing here is the oscilloscope. Let's start taking a look at the device. The device is turned on in front of you now, and only one channel is active. I can't stop admiring this huge, awesome display because I know how much oscilloscopes with a similar display with the same resolution and size actually cost. Believe me, it's definitely not cheap. Here, all the information is right in front of you, everything is accessible. Yes, there are some minor things, but again, that's just a matter of getting used to it. If you need to dig into certain parameters or use auxiliary options, of course, you'll have to go through the settings. But otherwise, all the main features are available and right in front of you. The horizontal sweep control is especially convenient. We can change the time just by tapping back and forth, and everything adjusts perfectly. Let me repeat, the display is very responsive. There are no issues with the controls here. So where should I start? Honestly, there's so much here it's hard to know where to look first. Well, let's go in order. Let's start. Channel settings are identical for the active channel. In this case, it's the first channel, the icon is highlighted. And for an inactive or disabled channel, you don't see this. Here are the settings. This is the basic set of options. Here we can limit the bandwidth, select the input type, choose the required divider, and enable or disable the channel. The third parameter is for the horizontal or time-based settings. We can select from the table or manually like this, which in my opinion is very, very convenient. Next is the fourth parameter. Here we can set the oscilloscope's resolution. The sampling rate is also displayed here. This parameter is not selectable because the oscilloscope manages this value automatically. Any digital oscilloscope only uses the maximum sampling rate in the upper frequency range. So, if you are analyzing some slow processes, the sampling rate will be minimal. Next, we have the signal generator. The generator operates independently from the oscilloscope, which is also very convenient. Overall, using and controlling the generator is very, very convenient. The only thing is, to change the waveform, you have to tap this tiny little icon. It's not very convenient, and sometimes it's hard to hit it precisely. Here are all the waveform types. We'll check this in detail a bit later. Here, the selected waveform is displayed, and the frequency is shown at the top. With these cursors, we can switch between the digits. And with the vertical cursors, we can set a specific value. The second parameter is amplitude, up to 5 volts. The third parameter is offset, and the fourth parameter is the pulse duty cycle. Well, some people might say that using these little things isn't very convenient. In that case, FNIRSI has made this feature. You press this icon and a keyboard pops up, so you can easily enter the values you need using the keyboard, which is very, very convenient. I skipped over the trigger settings, they're standard here. You can select the trigger channel and you can also choose the operating mode. That's single mode, normal mode, or auto mode, and you can trigger on the rising or falling edge. A lot of people are specifically interested in capture. For example, how well the oscilloscope can capture fast single pulses. This is actually important. We use this feature often, and of course we'll be testing all of it. Now, about these vertical icons, the top one is for freezing, or basically the stop button. In short, it stops the process.
Next is the auto adjustment button for the oscilloscope display. In other words, the oscilloscope automatically selects the optimal horizontal and vertical sweep parameters so that the pulse stays within the display, and everything looks clear, neat, and easy to see. These two buttons here are responsible for the vertical sweep.
So we simply adjust the voltage scale. We also select the channel depending on which channel we want to make these changes for. Well, in this case, let's use the first channel. Take a look here. It might seem that when we press the plus button, we're increasing the voltage, or more precisely, the value per division on the vertical scale, and accordingly, pressing minus decreases it. but actually the opposite happens. Alright, let me try to focus now. Here, look, it says 500 millivolts, right? We press the plus button and it actually decreases, and vice versa. So it's not really set up the way it should be. Maybe the manufacturer had their own reasons, or it's just a mistake. Or maybe I'm missing something, I don't know. But that's the point. And then they're setting the trigger in the middle. And then there's this T button which only does one thing. Maybe it's meant for something else, I just didn't get it. When we press it, everything here disappears. Honestly, I thought these were some trigger settings. I really don't understand why they did it this way. Alright, but that's not the main point about this bottom button and its purpose. I mentioned that it's not clear what it does, but actually it controls the trigger level. It's all set up pretty conveniently. Of course, you could do without it. You could just move it and set the desired trigger voltage directly. But in that case, you might accidentally touch these buttons with your finger and change something. But here, when you press this, the buttons disappear, and you can easily set the trigger level. Honestly, that's a pretty smart design. Here's a nuance you should be aware of. If you set the time base to 50 milliseconds per division or more, the trigger function disappears completely, and cursor measurements are also unavailable. To be fair, I should note that almost all oscilloscopes I have, and not just mine, have this same quirk. In other words, with a slow time base, these functions disappear. Well, it depends on the specific oscilloscope. For one, it might happen at 50 milliseconds, for another at 100, and for a third at 1 second. It all depends on the particular oscilloscope. Here's what I want to check. Let's say I still need to study some slow processes. I've set it here to, let's say, 100 milliseconds. Next, I do the following. I see a pulse and hit stop. Is that possible? Yes, in this case, we can use cursor measurements. So basically, you can set a very slow time base, carefully catch the pulse, and then proceed as needed. Yes, here everything works great. You can really stretch it out if you want. You can use it in whatever way you need, whenever you need it for your specific purposes. That's really great. Otherwise, damn, it just wouldn't work at all. That's fine. Okay, I missed 2 more points. This little dot here drops the beam to 0, meaning right in the middle. And this fast or slow mode actually lets you move the beam much more smoothly, or conversely, in a much more rough, abrupt, and uneven manner. The exact same functions are available in analyzer mode as well. So, about the icons at the top. Scale, it's just scale no matter where you are. There's nothing to explain here. Next, aperture. I don't know why the Chinese called it that. It's just for saving the image. When you save, everything gets recorded to memory. We'll take a look at all of this a bit later. These buttons, or rather, these icons, are responsible for cursor measurements. I've always been a fan of classic oscilloscopes with knobs. It's quick and easy to change settings and perform other operations. But when you have an oscilloscope like this with a huge display and a super responsive touchscreen, honestly, using the cursor measurements is just a pleasure. It's much faster and way better than using knobs. I have to admit it, because you get used to good things quickly. Everything is really well done. The next feature is called Browser. No, it's not the kind of browser you're thinking of. It's more like a gallery. From here, you can conveniently access previously saved signals, images, and other related items. Here's what I've saved. Actually, there were more pictures, but I deleted some of them. This is what it looks like. Naturally, you can transfer everything to your computer. It's all pretty convenient. Here, we can either delete the selected item, or simply return to the main screen. The next mode is called Functions. This is where we can enter the spectrum or frequency analyzer mode, and we can also adjust the beam brightness. It's not very noticeable, but the brightness does change a bit, and to me the thickness changes a little as well. We can enter the XU mode. We can also play around with the colors a bit, depending on what you like. We can turn the grid on or off. Next are the system settings. Here we can clear the device memory, select the preferred language, reset everything to factory settings, set the automatic power off time or disable this function entirely, perform a system calibration, and remember, system calibration must always be done before putting the device into operation. And then there are the safe settings. That covers the main settings of this device. Now let's take a closer look at its functionality. Before use, you need to do two things. First, perform the calibration available here, and second, calibrate the probe. To do this, you can use the built-in generator that's provided, meaning you can use it as a reference. You need to set a square wave with a frequency of 1 kHz and feed it to the oscilloscope input. The amplitude can be set from 1 to 5 volts. Next, for example, you can press the auto button if you don't want to mess with the sweep parameters, and the device will give you a perfect display. Well, just a little bit. By the way, I haven't calibrated anything yet, but I can see a slight droop on the leading edge, just a little, which can be quickly compensated. For this, you can use the standard plastic screwdriver that comes with the probes. I would ask the guys from FNIRSI to include yellow rings in the kit in the future. What am I talking about? I completely understand that FNIRSI most likely buys the probes from an external supplier and doesn't really pay attention to this detail. Well, it's a small thing, guys. Yes, I'm nitpicking, but still it would be nice to have everything just right. So these little rings or circles that come with the probes aren't just for looks. They're used to mark the probe so you can later tell which channel each probe is meant for. Accordingly, they're color-coded to match the channel, because each probe is individually calibrated for a specific channel. In this case, it's yellow and blue. I've already marked the second channel with blue, but there's no yellow ring in the set, and I've never seen one included with any oscilloscope from FNIRSI. I have a lot of them, and I brought almost all the stock probes I have, and I haven't seen a yellow one anywhere. There are red ones, all sorts of different colors, blue as well by the way, but no yellow. I'd like to draw your attention to this. It's a small thing again, but it would be nice for everything to look good. So I've already calibrated the probe, and now we're doing the system calibration. All calibrations are done. Now we can get to work. Let's start our tests, and we'll begin with a generator. I should note that during almost all of the tests, I'll be using my main portable oscilloscope as the reference device. It's from a much more high-end manufacturer, and it's a lot more expensive. Of course, it's a bit old, but I trust it completely. I've never had any issues or problems with it. I'm mentioning this because the bandwidth of this device is only 60 megahertz. The FNIRSI claims 350, but we physically can't even reach those frequencies because we don't have a high-frequency pulse generator. But the sampling rate of this device is exactly 1 gigahertz, an honest, true 1 gigahertz. Alright, let's set the generator to an amplitude of 5 volts peak to peak, and a frequency of 1 megahertz right away. The signal is a square wave. We press auto here and auto here. There we go. We can see that everything is fine. Both devices handled it perfectly. Let's adjust it a bit here so the signal is more complete. And here, basically, you can do the same thing to get a more or less similar signal. We can see that at 1 megahertz, the generator has no issues, really. Well, there are some minor ones, yes. We can also notice on this oscilloscope that the display is similar. I should note here that the FNIRSI in particular displays all this even more beautifully. There's really no doubt about it, because the phosphor technology here adds a certain unique analog charm. Plus, the display itself offers better color reproduction and, of course, a noticeably higher resolution. But still, these small oscillations are very, very clearly and quite distinctly visible on both of the devices. That's fine, it's completely normal. Alright, now let's increase the frequency a bit. Let's say 3 megahertz. Well, we see exactly the same signal. Notice you can see a bit of a decaying oscillation at the bottom, and the same thing at the top. Basically, the signal still looks very, very much like a square wave. Given that the frequency is quite high, everything is fine. The signal is at 4 megahertz. These oscillatory processes, something like a kind of ringing, have become more pronounced. The signal is definitely distorted, but it's still a square wave. It's not a sine wave yet. So as for the amplitude, damn, we haven't taken any measurements. At the peak, my device measured 5.28 volts. Damn! Exactly 5.28 here. So once again, I completely trust the readings from this device. This has been checked multiple times with more precise instruments. But in this test, the FNIRSI is kind of our test subject, and as we can see, there are absolutely no problems. So as for everything else, basically everything is fine too. This device can take more measurements than the FNIRSI, but I didn't display all of them. We're only interested in the main ones, peak to peak and max RMS. Here we have an RMS of 2.32, which is what the FNIRSI measured. For megahertz, by the way, the frequency counter shows exactly the same thing here. Alright. Where is it? 2.39 here, 2.32 there. Perfect, guys, perfect. So the device is able to measure correctly. This is very, very important because I've come across the opinion that an oscilloscope isn't a measuring instrument, but more for visualization. That's complete nonsense. An oscilloscope is both a research and a measuring instrument. So, well, at these frequencies I don't see any problems. At least not with the oscilloscopes. Alright, let's increase it a bit. 5 megahertz. Okay, everything is correct, 528.29. Here it's a little higher, 2.32. Our RMS is 2.36 here, and the generator seems to be handling it. So for now the signal is still a square wave. Surprisingly, it handles 5 megahertz just fine. 6 megahertz. The signals are completely identical, absolutely identical. FNIRSI uses some kind of smoothing. I think I've turned everything off here, and the bandwidth isn't limited either. Well, that's just the effect of an analog oscilloscope. A lot of people will probably like it. Yeah, the signal is pretty much the same. Alright, 7 megahertz. At 7 megahertz, we don't see any significant signal distortion. The amplitude isn't understated. Notice this is important. Well, it's actually a little bit higher, but only slightly. So here the RMS is 2.29, 2.24, also staying within the margin of error. Both devices display the frequency correctly. 7 here, 7 there. Awesome! Alright, let's keep going. Okay, let's go straight to 9 megahertz and see what happens there. Well, yeah, this is already, well, not exactly what we wanted to achieve in this situation, but still, it's something interesting to observe and worth noting. Up to about 7 or 8 kilohertz, the signal is more or less normal. At these frequencies, some problems start to appear, but we can see that there isn't any significant rounding off. That is, the signal still reminds me of an under. The most important thing is that the amplitude stayed the same. It was 5.28 here, and here it's 5.3 something. Here again, it's important to understand that most likely, even with very similar settings and exactly the same sampling rate, the devices can still operate at different speeds in certain specific modes. And one device might, for example, pick up some interference or a spike that the other simply doesn't notice. That's completely normal because these aren't identical devices. Even with identical devices, this can still happen. So basically, we don't pay attention to that. Well, also, in principle, the RMS value is a bit understated. FNIRSI also picks up on this. Everything's cool. We'll set the maximum to 10 megahertz. Alright. Well, here, of course, as expected, things are even worse. But again, we don't see a complete roll-off. We don't see any significant, sharp drop in amplitude. And that's really, really great. Yeah, it doesn't go any higher. Man, this time it seems like the guys aren't really exaggerating. Basically, the generator is decent. Alright, let's try a sine wave now. I think I'll just go ahead and look, you can actually pry up this keyboard with your finger just by gently lifting at the edge. It's not in the most convenient spot since it's tucked away a bit, but you can still get to it if you're careful. So let's set the sine wave to 20 megahertz, making sure the frequency is set precisely to that value. 20 megahertz, the amplitude is still 5 volts, 50%. We see 5 and 5 volts here, 5 and 52. Well, it fluctuates a little, but that's normal. 5 and 5, it's basically the same here. Everything is perfect. So at a frequency of 20 megahertz, we don't see any signal drop off. Let's set it to 30 megahertz. Here, it's definitely worth stretching it out a bit. Just take your time with it. The signal jumps around a little, by the way, on both of them. Yeah, there's definitely some kind of smoothing happening here, or maybe it's that phosphor effect. You know, something like an afterglow or lingering trace. I'm not even sure exactly what to call it. Here, the signal is jittery, while over here it updates faster. And here it's smoother, kind of like an old tube display, but you can still feel that the signal jitters a bit. Let me show you up close. Darn, it's not really visible on camera, but it's definitely there. On this oscilloscope, you can clearly see how it jitters just a little, just a bit. And it's jittering horizontally, so the amplitude is fine. Well, maybe in this case the oscilloscopes just can't provide a perfectly still image. Alright, let's not pay too much attention to that either. At the very least, the frequency is 30 megahertz, and now everything matters, including even touching these probes. Alright, let's zoom in. 40 megahertz. Here you can clearly see how the signal starts to jitter more, but here it doesn't. Is it possible? It's possible. I haven't tested this oscilloscope at such frequencies because, as I said, I didn't have a reference generator, and it's possible that this is already close to its limit. And that's actually the case. 60 megahertz is the maximum for this oscilloscope, and since we're approaching the bandwidth limit, this kind of thing happens. But the FNIRSI still has a long way to go before it reaches its bandwidth limit, and it's doing just fine. So it might even be significantly better than my device here. Well, on paper it's definitely better, but in reality, that's something we still need to find out. The display on the FNIRSI does look nicer, much nicer. Both devices started showing slightly higher peak-to-peak values, about 7 volts here, and the same, around 6.6, maybe 6.7 volts on this device. This means that our generator slightly overstates the amplitude at these frequencies, which is expected because we're already close to its limit. And now it's starting to understate it. You can clearly see that. Right now, up to about 40 megahertz. we're seeing an overstatement. So there's this intermediate range where the amplitude is overstated, and then suddenly, there it is, 7.1 volts, and then it just starts to drop. So, if the frequency is above about 41 megahertz, it keeps dropping and dropping, and at 50 megahertz, interestingly, we still have 6.4 volts, so it's not a particularly serious drop. Man, I just can't believe, guys, that everything here is really this perfect. They claimed 50 megahertz, and there really is 50 megahertz here. It's hard for me to believe it when it's FNIRSI, but the facts speak for themselves. Let's state the fact. The generator outputs a 50 megahertz sine wave without any noticeable drop in amplitude. There is a slight overshoot. Yes, that's present. Both devices are registering exactly 50 megahertz. The sine wave isn't distorted. Everything is great. Let's consider this the bandwidth limit of this oscilloscope, which is why the signal jitters a bit. The same thing is happening here too, but the jitter isn't as pronounced. Again, considering that we've set the maximum possible frequency. All in all, I tip my hat. I've set the signal to 4 megahertz, a square wave, and now let's play around a bit with the duty cycle. Here you can see that it doesn't go below 9.6. So, 9.6, right? And what if we change frequency? Well, let's say 1 megahertz, it does go lower. So, that's a little quirk to keep in mind. Take note, I just happened to notice this by accident. Depending on the frequency, the duty cycle might not be fully adjustable. Alright, let's set it to 3, for example. Pressing auto, let's see what happens. Yeah, everything's great, everything's working perfectly. Yeah. I don't even have any doubts here. Yeah, it's all the same. So, right. Where's our frequency? Alright, peak to peak is 5 and 24. 5 and 15 is what the FNIRSI shows. Okay, well, everything else is fine. 3 and 22. 3 and 22. Did I not display it here? I didn't display it. Alright, we'll just have to take FNIRSI's word for it. Okay, well, everything else seems pretty normal too. Obviously, with such tiny probes, the pulse is going to be a bit rounded off, and that's completely normal. At lower frequencies, of course, there will be fewer problems. For example, like this. Let's say right now our signal is at 100 kilohertz, and as you can see, everything is as flat as possible. Really, really nice pulses. So overall, the generator is working fine. Let's try setting some other waveform types and see what else we've got here. Alright, the signal is again at 50%. Well, we've already checked the sine and square waves. So, triangle. Either way, the frequency is 1 megahertz. The triangle signal looks fine, basically. Next, sawtooth waves. Looks good. Man, something needs to be done about this icon. Raise it up a bit. Make it at least finger-sized, because right now you have to pick it with a toothpick. Steps is labeled. Staircase. Okay, this is after half-wave rectifier. Well, man. What is man? Index. This is an exponential signal. We call this 1 bell. Well, honestly, it's a pretty complex signal because both the amplitude and the frequency change here. Root. This one is root. Alright, next. Audio. You can also see that the signal is jittery. So, it's basically fine. Sample. DC means direct current and hold. Overall, I don't see any major issues with the generator. On the contrary, I actually really liked it because its specs seem to match what's advertised. Studying Lysage's figures. The oscilloscope is operating in dual-channel mode, XY sweep. One channel receives a signal from the internal generator, and the other channel gets a signal from an external generator. Frequency is 1 kHz, sine wave. And we get this beautiful ellipse. The image is very vivid, and here we can play around a bit with the color temperature. Overall, everything is very clear and visually appealing. Let's check the operating modes of the trigger. For this, I'll use my homemade spot welding machine, my Weld version 2.0 Pro. After pressing the pedal, it will generate 2 welding pulses. The first one lasts 3 milliseconds, then there's a 60 millisecond delay, and the second pulse lasts 10 milliseconds. All of this goes to the shunt. In this case, a 100 amp shunt with a voltage drop of 75 millivolts is used. An oscilloscope is connected in parallel to the shunt, so it will capture these pulses. We can perform various manipulations and measurements of amplitude and duration, which allows us to know the welding current and much more. Let's check the trigger now. We have the single trigger mode set up like this, and we press the pedal. Let's see if it captures this pair of pulses. It captured them without any problem. No problem at all. Let's do it one more time. Same thing again. And one last check. Perfect. All 4 times it captured perfectly. Next, we can use the cursor measurements. And, if needed, we can scale this. And now, in theory, knowing Ohm's law, knowing the shunt resistance and so on, 1.4 volts, guys. Well, actually, the capacitors aren't fully charged right now, not fully charged. Actually, I did measure this current, and at its peak, it's 1.48. The oscilloscope measured 1.4, give or take the experimental error. Everything is perfect. And considering that, most likely, well, this is probably a more accurate representation. There it is, the peak. Just like that, 145. Perfect. These are accurate readings. There are basically no questions about that. Next, we switch the device to this mode. So, okay. Let's set it to automatic. Next, let's turn off the cursors. Now, the regular mode, and we do the same thing. It captured it. Now we press it again. It should capture it again, in theory. The image just refreshes like this. For clarity, we can switch back to auto and go here again. It captures it, guys, no problem. And of course, you can perform the same measurements. Now let's talk about the other functions this device has. Specifically, let's take a look at the spectrum analyzer. I'll try to explain in detail and in simple terms what a spectrum analyzer is for, especially for people who have heard about it but haven't really looked into the details. A spectrum analyzer is generally used to display the frequency composition of a signal. It allows you to detect things like harmonics, various types of noise, and high-frequency spikes that you can't see or are hard to see on a regular time domain waveform. Here, the spectrum analyzer is, I'll repeat, a secondary feature, but it's still quite suitable for many types of research. So, basically, we have certain signals. This could be just one signal or multiple signals at different frequencies. And with an oscilloscope, you won't be able to catch or study everything. But with a spectrum analyzer, we can see the peaks where, for example, there is broadcasting. In particular, it's used for transceiver devices, for tuning radio equipment, and it's also used in telecommunications. Let's start by looking at all the functions available here. The return icon, accordingly, exits the spectrum analyzer mode. We'll talk about the functions a bit later. There are quite a lot of options under this section. The diagram, just like with the oscilloscope, is simply saving whatever is on the display. There are also cursor measurements. Here, two cursors appear, and we can select a specific section in more detail and study it. So, it turns off the same way. Auto calibration, just like with the oscilloscope, and freezing the readings. Let's look at other parameters, which are by no means secondary. In fact, these are the primary parameters for almost all similar devices. The first one is decibels relative to 1 millivolt or dB millivolt. It shows the signal amplitude on a logarithmic scale. Simply put, this is the input signal level. Here, accordingly, we can set the required value. Right next to it, we have the attenuator settings. An attenuator is a device that reduces the signal strength. For example, if you're studying some high voltage spikes or something like that, you need to reduce all of that to attenuate it in order to protect, say, the device's input circuits. Next are the following three parameters. We can set the start and end of the frequency component, meaning the beginning and end of the frequency range, as well as the center. This is useful if you need to study a specific section of the overall spectrum. I think that's all clear. The functions menu. Here, the first thing we see is the FFT length parameter. You can choose between 4, 8, 16, or 32. Basically, this is the resolution or the number of points used to build the spectrum. We'll talk about this in more detail a bit later. Now I'd like to talk a little bit about the FFT parameter, what it is, how it works, and why it's needed. Basically, all spectral analysis is based on FFT. This is the fast Fourier transform. This transformation converts a signal from the time domain to the frequency domain, showing its frequencies. As before, you have an oscilloscope, signals with various shapes, frequencies, and amplitudes. Of course, with an oscilloscope, you can study a specific signal and take some measurements, but when you're dealing with a large number of signals, or a signal that's noisy, for example, the oscilloscope becomes useless. You need to convert all of this into the frequency domain and study it in more detail on the spectrum analyzer's display. As peaks, you can see the entire spectrum and all the signals that make up that spectrum. This is very convenient in telecommunications and radio equipment. Without this, without a spectrum analyzer, it's simply impossible. What exactly is FFT length? FFT length is the number of points the device uses for analysis. The greater the length, the higher the frequency accuracy, meaning better resolution. You'll be able to see small peaks that are impossible to spot at lower resolutions. But the higher the resolution and the more points there are, the slower the readings will update. If you only need a basic, non-detailed analysis, you can lower the resolution and the device will work quickly and smoothly. A bit later, I'll show you what this looks like in practice. Accordingly, there's also a calibration option here. There's a 3D display like this, and there's also a waterfall view. Here we can see those main peaks. You have to admit, the guys from FNIRSI really put in the effort to make it look great. It looks truly professional. But since we don't have a high-frequency generator, of course, we could use the factory generator. A bit later, we'll do that. Set a specific frequency, and that frequency will show up as a corresponding peak. But I have this homemade radio bug. A bit later, I connected it to the input of our spectrum analyzer, and overall, we'll be able to study the harmonics of the quartz crystal that's installed here. And now for some practical application. I connected the antenna of the radio transmitter to the input of our spectrum analyzer. Now we're turning on the lab power supply, which powers the transmitter, and we can see the full frequency spectrum. To start, it's worth narrowing the range a bit for a more detailed analysis. I'll point out first that the quartz crystal installed in the transmitter has an operating frequency of about 13.5 MHz. So let's set the start at 10 MHz, and the end can be, well, somewhere around 200 MHz. Awesome! Everything you see here are the harmonics of our quartz crystal. And now we can use the cursor measurements. So the FFT length is currently set to, let's see, 16K. That's a medium value. We could make it a bit smaller. And we move the first cursor. Obviously, to aim more precisely and study a specific peak in more detail, you can narrow it down a bit, meaning you focus on a smaller section of the frequency range and set the required bandwidth using these limiters, which help you define exactly how wide or narrow the area you want to analyze should be. So, let's see, it's showing 13.6. Considering that we aimed by eye, I think that's really, really cool. Let me remind you, our main frequency is 13.5 MHz. Next, the second peak is the second harmonic of the quartz. It should be around 27 here. Yes, 27 MHz. And, accordingly, here it's another 13.5 added. It's not very visible, it's really small. 41, 41, and so on, increasing gradually. Okay. Here we get somewhere around 80 something, or so, and so on. Got it, I think so. Well, of course, you can use the second cursor too. Let's say we need to study this particular part in more detail. Here we have, well, let's say from 75 to 82. So, here we set the initial starting point at 75 MHz, and then at 82 MHz here as indicated. And here it is, actually, our peak, 81 MHz. So you can't see it? You can't see it. Here it is, here it is. Got it. Here you can more clearly see what changing the resolution does. Well, 4K is when you need everything fast, but the number of points is small. This is the kind of image we get. Again, for many tasks, this is more than enough. Next, a slightly more detailed image. Now it's a good image and the most detailed one. Here we can clearly see that there is already some lag. But on the other hand, we can study a lot more peaks here. This thing, fast, slow, just lets us move the cursors more quickly and efficiently, or more precisely and in more detail if we need to study some small, short peaks. I think this will be useful. That's regarding the spectrum analyzer. Overall, I really like how simple it is to use. Everything works as intended. I didn't notice any bugs or issues. You can get the hang of it quickly. Even someone using a spectrum analyzer for the first time will be able to fully master this option in a very short amount of time. The next, fourth and final function of our device is the frequency analyzer. It's an indispensable device if you work with analog equipment, all sorts of filters, amplifiers, studying resonance, and so on. It allows you to quickly and efficiently test the device under examination within the required frequency range. After that, you can promptly build graphs, create professional instructions, or carry out other measurements. Basically, in simple terms, it's an automatic way to see and even measure how your device performs at different frequencies. Overall, it can show how the signal is amplified, attenuated, or distorted depending on the frequency or frequency range. Here's how to use the device and, in general, how it operates in this mode. All the inputs and outputs of the device are used here. The first channel of the oscilloscope serves as the input. It is connected. Let's take a low-frequency amplifier as an example. it is connected to the input of the amplifier under test. At the same time, a signal from the generator, which we'll call the reference signal, is also connected in parallel to this same amplifier input. So you set a certain frequency there, for example 100 Hz, and connect it in parallel to the first channel and to the input of your amplifier. The output of this amplifier under test is connected to the second channel of the oscilloscope. What does the analyzer do in this case? Its task is to automatically generate a signal, sweeping through frequencies within the set range. For example, you need to test your power amplifier in the frequency range from 10 Hz to 1 kHz. You set this limit, and it automatically cycles through all those frequencies. Then it compares the input signal on the first channel with the output signal on the second channel. Based on this, it builds a graph. This happens very quickly, where the horizontal axis represents frequency, and the vertical axis, accordingly, shows amplitude. This, in turn, allows you to evaluate the device's behavior at different frequencies. For example, you can assess the bandwidth, roll-offs, resonances, and so on. You can also specifically look at, for instance, the cutoff frequency, where the signal drops by -3 decibels. In other words, that's the edge of the bandwidth. You can also evaluate the sections where the signal is amplified, weakened, or just stays flat. I think that's clear. Well, it's a standard amplitude frequency response. To start, let's understand what functions and features this meter has. Well, the return button is, obviously, for going back to the main screen, to the oscilloscope display. Calibration function. I strongly recommend performing calibration before each test, because this way the system compensates for all the factors and characteristics, as well as losses that occur in the cables, wiring, and connections. In this mode, for calibration, the oscilloscope channels are generally connected together with the generator. The diaphragm, as in all other cases, simply saves what is on the display. Cursor measurements are also available. This analyzer has two operating modes, cyclic scanning and single scanning. This parameter can be compared to the trigger mode in the classic oscilloscope. So, right now, cyclic scanning is being performed. But if we switch to single scanning, the device will capture and freeze the readings. I think that's clear. And next, okay, we need to exit from here. And then there's the stop button. At any moment, you can activate it to capture what's on the display for further analysis. Let's take a look at the parameters we have at the bottom. First up is amplitude. This is the amplitude of the excitation signal, or the amplitude at the output of our generator. Next is the parameter called compensation. Basically, it adjusts the DC component of the signal within a range from -2.5 to +2.5 volts. Next, we can set the start frequency for scanning and the end frequency. In other words, the scan will be performed within the specified range. After that, we have an item called quantity. This is the number of steps or samples from the start frequency to the end. You can adjust this value from 20 to 500 points. Well, here, just like in the previous case, with 20 set as the minimum right now, the scanning is done pretty quickly. If we set, for example, 100, then of course there will be more points. Everything will be easier to see, but the refresh rate leaves much to be desired. I won't even mention what happens if we set. Well, let's set it to 500 points here and wait to see how long a full scan takes. You can time it there. For a moment, I had the impression that the device had frozen, but no, you can see that everything is working fine. But again, the scanning time is quite long. There was a bit of a mishap with the frequency analyzer. I was planning to show you its real-world application. I grabbed a couple of Class D amplifiers, meaning I wanted to demonstrate by removing the covers from Class D amplifiers. I played around with them a bit. Let me say right away, the analyzer works and is quite convenient to use, but during my experiments, I'd burned out a couple of these cheap Class D amplifier modules. This one is completely shorted, and the other module, currently connected, only works for about a second when powered on, and it's unclear. Either it goes into short circuit, protection mode, or something else is wrong. Basically, power consumption is zero. I found another one of these little modules, also a cheap Chinese Class D amplifier, and it turned out to be completely non-functional. So I'll need to restock my supply of these small, Class D amplifiers. In the near future, probably a few days after I publish this video, I'll do that, because I feel like I didn't fully demonstrate how this function works. I'll find my homemade Class AB amplifiers. I have some Azars and Slaps, not sure if they're in storage or here in the workshop, so I'll have to dig around a bit, get ready for the test, and we'll record the frequency response of these amplifiers. I think you'll find it interesting. At the same time, we'll talk about everything in detail. I tried to figure out what the catch was right up until the end. When it comes to the company FNIRSI, as they say, the devil is in the details. I won't deny that they have some pretty decent devices for the price, but there are more of those with a lot of rough edges, beginner's issues, whether it's the electronics inside that feel cheap, or the software. But with this device, over several days, I tested it, reviewed it, filmed videos, and used it at the same time to figure out what serious flaws or general shortcomings it might have. And I didn't find anything out of the ordinary. The device is perfectly made and very convenient to use. All the options work, and everything matches the stated specifications. And honestly, right up to the end, I just couldn't figure out where the catch was. I thought that maybe at the very end, when I opened up the device, I wouldn't like what was inside, and then everything would make sense. But to say I was surprised would be an understatement. Guys, the internal build is elegant and very well done. Unlike other oscilloscopes from FNIRSI that I've tested, this one was clearly engineered by professionals. Alright, let's start from the beginning. These side panels, as I mentioned earlier, are metal, but judging by how light the metal is, it's probably aluminum, though there's a tiny chance it could be titanium, but I doubt it, since titanium is more expensive. Anyway, that's not the point. On the sides here, there are light filters for this stand. Oh, sorry, for the backlight. Inside, there's a huge lithium polymer battery with an 8 amp-hour capacity. And by the way, the device is pretty power hungry. So during the review, which took a few days, I had to charge it about 4 or 5 times. But to be fair, I was filming a whole lot. So, regarding the battery, all the wiring here goes directly from the battery. It's flexible, elastic wires and silicone heat-resistant insulation. Really good quality overall. The fan itself is actually part of this stand here. And then there's the internal components of the device itself. What really stands out here is the generous amount of gold. We've got gold-plated traces here. It's everywhere, and that's just how it is. Well, I know a little bit about this, and most likely this is a single-layer gold plating, so it's not the thickest, but it's still gold-plated, and that definitely deserves a lot of respect. It looks premium, and of course, it won't oxidize over time. Overall, everything here is fine. The board has a shiny, golden color. And honestly, it's not clear, but most likely there's some kind of lacquer coating or something like that. So it's a bit of an unusual board, although that's not really all that important. Let me show you. This is how cool it looks. What's the best thing you liked? I showed you an oscilloscope from FNIRSI before, which was really poorly designed in terms of the layout of the input circuits, among other things. Basically, the oscilloscope input is somewhere over there, and the signal travels all across the board before it gets to the ADC and so on. So, it's quite a long distance, and that's obviously really bad. It's not normal, because it will definitely affect the signal. And honestly, nobody does it that way. But here, real engineers work on it. You can really feel it, because absolutely every part is under shielding. Here's our generator under a shield. These are the oscilloscope channels, and here's something else under a shield. And look at this beautiful gold plating. By the way, the board here is multi-layered. Naturally, it's extremely thick. Just take a look at this. It's at least 2, maybe even more, millimeters thick. So it's a non-standard, and therefore expensive, board. Well, more or less, I know the cost of boards like this. And of course, if you buy them in bulk it'll be cheaper. But still, the board isn't cheap. So, as for the components, I'm not really going to say much here. These are most likely our ADCs. There's no real marking on them, maybe. Well, if you dig around, you could probably find some information. But there's just a small code marking, 2445, yeah, most likely. It's not clear what it is, you know, kind of typical for FNIRSI. It's fine, really, let's not nitpick. As for the other controllers, honestly, I haven't really looked into them. I just want to show you what's inside. If anyone's interested, you can dig into the datasheets yourself and figure out what's what. On the other hand, I'm not going to open that up, because there'll be ribbon cables, shields, and most likely we won't find anything there except maybe some small stuff. All the main components are located right here. This one is most likely the main controller. Or maybe that's not the case, I can't say for sure. But damn, overall the board is made elegantly. These chips here are placed very close to the input circuits. And overall, this main processing unit is the same way. So, basically, there are several microcontrollers here to control different things, different functions. Under this thing, most likely, damn. It's a shame these shields cannot be removed at all. They're soldered on, unfortunately. Most likely, the charging system is located in this part. Here we have, right here, a Type-C charging input port. Well, the battery connects here, and the charging system is located here. It's definitely going to be a switching impulse system because the power is pretty high. This is our backlight. Damn, there really is nothing to complain about here, you must admit. There's truly nothing to criticize. It's made very, very impressively. This is a worthy product, especially considering the price. Well, I guess it's time to sum things up. This is the coolest device I've tested lately, and without a doubt, it's the coolest, most advanced, top-of-the-line, and most bug-free device from FNIRSI. I remember quite clearly when FNIRSI was just starting out, releasing some pretty mediocre devices of questionable purpose and quality. That was just a few short years ago. But now, what I've seen from them is truly world-class, both in terms of build quality, overall functionality, and technical specs. It's a remarkable transformation. You won't find a device anywhere near this level, even with similar specs for this price, because this is a 4-in-1 device, and everything here works exactly as it should. At least I'll say it again, after several days of active reviewing, using, and looking for flaws, I didn't notice any glitches. Maybe there are some very, very minor things I missed, but nothing significant that would affect how it works. But overall, this is an amazing device. I've almost never, or only in the rarest cases, tested the entire product lineup from FNIRSI. Everything they release, they reach out to bloggers and send it out long before the official, and sometimes even before the official presentation. So when they sent me this device, it wasn't even available for purchase yet, just so you know. And what's great is that FNIRSI always accepts criticism. We often correspond with the folks in China. Sometimes they send me new firmware, new manuals, and so on. And they know perfectly well that I'm one of their harshest critics. But in this case, honestly, there's nothing to criticize. Seriously. I really like this device, and I can even, something I rarely do, actually recommend it for purchase because I'm sure you'll like it too. That's all from me, friends. Don't forget to leave your feedback, rate this video, and share it with your friends. And as always, all additional information is in the description. Until next time, bye!